Hi, welcome back to this part of my video series here on converting this Volkswagen bus into all-electric drive. In our last video, what we got done was built this battery box and basically connected it all to do our first motor spin test. In this video, what I want to do is wire and program that Thunderstruck MCU to become the brains of our electric vehicle. What I mean by that is I wanted to control the charge port, the charger, the battery management system or BMS, and our state of charge gauge. Well, to do that, I'm going to show you how to wire it up. I'm going to show you some rewiring that I had to do to give some of those responsibilities to the MCU. And then I brought my laptop here because I'm going to show you how you can connect your laptop to the MCU to get statuses and do programming in it. And in particular, we're going to program two of the programmable outputs on that thing to do something custom for us. So stay tuned. Well, the first thing I wanted to show you is the wiring here. As you can see, I decided to mount my MCU to the lid of this new high voltage junction box behind my battery box here. As you can see, I've kind of got all this wiring just sloppily put all over the place and wire nutted and connected. I'm just really doing bench testing at the moment, and once I get that tested, I will clean that all up and organize it. If you're only interested in seeing how I set up and program the MCU, I'll provide a pinned comment and you can skip ahead to that section. But I think it's important to get the context of how I'm wiring it and why I'm wiring it to understand why I'm programming certain inputs and outputs in the way I'm going to do it. So to wire the Thunderstruck MCU, we have 4 terminals on it. We have 1 on each side and then 2 on the bottom here. Each one has a different number of pins. Thunderstruck does provide you with these I think they're Tyco connectors. What I need to do now is kind of give you a high-level rundown of all these different inputs and outputs here, and I'll show you how I'm going to use them. So starting with connector A, we have pins 1 and 2 being ground and 12 volt positive. These are constant power that I brought in a 12 volt from my fuse block that's connected directly to my battery terminal and a ground wire for the chassis ground. Pin 3 is a KSI, and the way I have that, I'll mention more about this later, but I've kind of redone all my KSI wiring. Right now, KSI, or key switch indicator, is really just the 12 volt coming off a fuse on my ignition enabled fuse block that's in my DC command center. That goes through my inertia switch. The inertia switch is just a switch that opens up when you wreck or roll over. So for the most part, that'll always be closed. And then that goes into here as the KSI. Now pins 4 and 5 are for the CAN bus. The MCU supports 2 CAN bus networks. The CAN 1, which is on connector A, and CAN 2, which is on connector D. CAN 1, I'm going to be using only for my battery management system. So the A123 measuring balancing boards, there's going to be 2 nodes or measuring balancing boards per module, and I have 6 modules, so that's 12 total. They'll all be parallel wired into those 2 CAN bus wires that'll go into pins 4 and 5. Now pins 6 through 9 are this IPO, IMO. I won't be using those. What that is it's a similar to CAN bus, it's a digital signaling type thing for certain battery cell measuring devices. And it's just not applicable for me because my measuring and balancing boards output CAN bus signals. So we'll just be using 4 and 5. I won't be using 6 through 9. And 10 is a ground. I don't really have any documentation on that, or I haven't seen anything on that. So for now, I'm not going to be using it until I need it. Okay, so that's connector A. Like I said, I'll be wiring up pins 1 through 5, and that's pretty much it. All right, connector B. This is specifically used for our current sensor. Now, I bought a current sensor called LEM from Thunderstruck Motors. They have 2 versions, a 500 amp and 1000 amp. I bought the 1000 amp one just to make sure I can go higher than 500 amps. What that is a donut shaped Hall effect sensor. I have it connected to the side of my distribution box, and I have my main positive 2.0 cable running through the sensor. There's 4 wires on the sensor that match up with the 4 wires in this connector. So all I did is just match up those wires, and that will allow the MCU to get current readings from that Hall effect sensor. Okay, so connector C is 5 inputs. Now, I'm not sure what pins 1 through 3 are. They're inputs 3, 4, and 5. I think in the documentation I read there's similar Hall effect type inputs, but I'm not going to be wiring those right now. All I've done at the moment is wire 4 and 5, which are our proximity and pilot wires. Now, if you saw my previous video on the charging box, you'll know that I had a module in there called an AVC2. And what that did was what the MCU can do here. If you put in the proximity and pilot wires from the charge port, it will automatically detect that proximity wire, which means we're plugged in, and then negotiate the pilot signal going out to the charger to turn on the charger and give us voltage so we can start charging. In addition to that, the AVC2 also had a relay in it. Notice I had wired up there. And that relay would turn on if the proximity was detected. And I used that to output a 12-volt signal to my DC command center, which used a relay to disable my KSI for the controller. Now, since I ripped out the AVC2, I just forwarded those proximity and pilot wires from my charge port all the way out and into my MCU now. But without the AVC2 and that extra relay, I no longer have the right logic to disable my controller when the charge port is plugged in. So therefore, what I'm going to have to do is program one of the outputs on connector D to do that for us. So let's talk about connector D, which is our final 8-pin connector that's on the right side of the unit here. Connector D is where we have all of our programmable outputs, and that's what we're going to be talking about in the next part. So outputs 2, 3, and 4 are all type binary outputs. True or false, they're basically switches, on or off. The way you use those is you can program different conditions within the MCU to say, hey, I want to turn this output on or off. What they're off, what it means is those outputs are open to ground. When they're on or enabled, they're closed to ground. Now, which ground is that? Well, that's pin 1 on connector A. That's our chassis ground that we brought in. So the way you use those is you can program to enable or disable them, but you need a relay really on the output side to actually utilize those. The way I would wire this up is if I program, say, output 2 to enable, what that would be connected to is the negative side of the relay coil. The positive side of the relay coil will be a positive 12 volts of constant power. So when this is enabled, when the ground closes, the relay will then click and close. And that's how you can use these to operate different devices. Now, output 5, which is on pin 6, is a special type of output. That one uses pin 5, or that 12 volt, coming into there. And the way I'm going to do that is just split the 12 volt on connector A pin 2 into this one as well. Now, output 5, you can again program, and it's like the other outputs, it's on or off, but instead of being closed to ground, being on, it simply turns on the 12 volts that you connected to pin 5. So off is 0 volts, on is 12 volts. Okay, so that's the overview of the wiring of all of those connectors, and let's now get started on looking at how we're going to program a couple of those outputs on connector D. All right, I brought you inside the car with my laptop here, and I'm getting ready to look at how to connect the laptop to the MCU so we could talk to it. When I purchased the MCU, it came with this cable that Thunderstruck gave me. Notice it has a USB on one end for the laptop and this audio jack looking plug to connect to the MCU. This is a serial cable. Now I'm on page 13 of the documentation here where it starts talking about the serial port, so let's get into that. Okay, so like I said, this is page 13 here, and notice that it talks about the cable here, and it says manufacturer of the cable, FTDI, and the model number as well. The reason I wanted to show that to you is if we go to the FTDI website, which is this one where they give you a link to the driver here, ftdichip.com. So we go over here, and I just wanted to let you know that if you do damage or lose that special serial cable there, this is the model number there, and this website will sell you a new one. Just be careful with it because it is $25. It's kind of expensive, but you can replace it if you need to. The driver page that they link to looks like this, and I just scrolled down here and I put click here to download the Windows 7 to Windows 11 driver. Or if you're on a Mac, you can scroll down to the bottom of the page and look for the Mac drivers. This universal driver is likely the one I downloaded right here. And all you do is download it. It's an executable installer package. You install it, and that's basically it. Okay, now that I have my cable device driver installed, and before I even hook up the cable or anything, let's go ahead and open our device manager here and look what current COM ports we have before we install our cable. To do that, hit the Windows key and then start typing device and open the device manager. It's part of control panel depending on the Windows version you're using. And what I'm going to do is look for ports. And notice that I have 5 COM ports here. I have 4, 5, 7, 8, and 9. Now what I want to do is install our cable here, and I'm going to go ahead and plug it into both sides, the computer on the USB side and on the other side, I'm going to hook it up to the Thunderstruck MCU on the left-hand side here. Okay. Now that we have that inserted, what I'm going to do is look back up at our screen here, our device manager here, and notice we have a new one called USB Serial Port COM10. COM10 is the one for this cable, and that's the one we're going to use. So just remember that. Okay, great. Now that we have our COM port identified and our cable all connected and ready to go, the next thing they mention is that you'll need a terminal application like Putty to talk to the MCU. Well, I happen to already have Putty installed on my computer because I'm a software developer by trade. But if you don't already have it installed, just Google search Putty for Windows and it's a free download. Once you download it, let's go ahead and open it. And it looks like this. Like I said, this is a terminal application program. It can connect to different remote computers or cloud servers using different connection types. For our purposes, we're simply going to use the serial connection type. So what I'm going to do here is click serial, and then I'm going to enter in on the serial line here my COM port. Now remember, my COM port was 10 for the USB cable. Now as far as the speed, what we need to do is refer back to our manual here. They give you a secondary manual on how to do what I'm showing you right now. In that manual, it explains that most of their devices operate on 9600 baud speed, but the MCU can operate at a rate of 115,200. So I'm going to go ahead and make that the speed for this. Now, before I just hit open at the bottom here, I'm going to save this so I don't have to remember this again. So what I'll do is in the Save Sessions box, I'll type in Thunderstruck MCU, and I'm going to hit Save. Now notice it saves it now into this list. So if I close the program, I can just click on this and hit Load, and it'll recall this information I put in so I don't have to remember it. So now that I have it loaded in here, before I click Open, there's one more thing I need to do. I mentioned all the wiring before, right? I have all that stuff wired up, but you can't actually talk to the MCU unless you have the KSI input enabled. And so, of course, I have the KSI connected to my ignition switch. So let me go ahead and turn on my ignition, and we should see the MCU. And I don't know if you can see it, but now you can see once I turn that KSI on, you can see it has an LED light there glowing green and red. Now we're able to connect to the MCU. So when I hit open on my Putty application, it'll open this window up. Now, nothing will happen initially, but if I click into the window and hit enter, it should give me a prompt. Notice that the prompt is MCU, which means it can start taking commands. So one of the commands we can do is flip from the MCU prompt to the system prompt by typing SYS or sys. And now our prompt changes to system. Now we can do some of the system commands. This is where we do configuration. One of them being just like show config, which kind of shows an overview of some of the configuration. Notice here it'll show you what's currently configured, which is just that we have A123 batteries running on CAN bus 1 at the bottom there. We have our CAN bus 1 and 2 baud rates set to 500 and 250, and we have a couple inputs set, which are our LEM or current sensor inputs. So now we've successfully connected to the MCU. Let's now talk about programming some of our outputs. All right, so the first output that I want to program is an output that's going to control our battery pack contactors. In my previous video, I showed you how when I did my motor spin test, where I hooked all these contactors up to a fuse panel back there in my distribution box down there, and that way each one of these can have a fuse on it to use as a disconnect, so I can disconnect any of these parallel packs. What I need to program is the logic behind turning that fuse panel on and closing these contactors. When I did the motor spin test, that logic was simply, I hooked it up to a 12 volt positive coming off the KSI or the ignition switch. That way I could just show you the motor spinning. But it's a little more complicated than that. When I turn on my ignition switch, I do want those contactors to close to be ready for the startup of the controller, but I also need them on when the car is off, but only when I'm charging. So I've already done some preliminary wiring in here on the MCU and in my box here. I've added some terminal strips just to organize grounds and hots and things like that. But I also added this relay there. What I'm going to do is I'm going to use output 4, which is one of outputs 1, 2, 3, and 4 are all kind of the same, where you can program them to close to ground, right? And I mentioned before that you would typically use a relay with the negative part of the coil coming out from this output to actually control something. That's exactly what I'm doing here. So output 4 is this gray wire here, and if output 4 closes to ground, this gray wire is hooked up to the negative side of that 12 volt relay right there. Now the positive side is hooked up to just one of these yellow wires, which is constant battery power. That's bridging both the positive side of the coil and the constant on the relay, because the relay is going to output 12 volts as well. If our switch goes to ground and clicks the relay on, it's going to click to the normally open position, which is this red wire here, which is then tied into our fuse block here. So the first thing I've done here is I've connected my Putty session back to my MCU, and I'm in the sys prompt. So what I'm going to do is I'm issuing a command called sh, and what this does is it outputs all of the possible inputs and outputs and what's going on the different connectors that we've talked about in this video. As you can see, we have the inputs for the Hall effect. We have a proximity and pilot. Right now, the proximity is at INF, meaning it's not detected, and there's no pilot. And none of our outputs have anything mapped to them. Okay, so how do we want to program what I just mentioned onto output 4? Well, the first thing I did was figure out how can I know from the MCU whether our proximity is plugged in or whether or not the KSI is on. Well, the first thing we can do is we can go to this page on the Thunderstruck manual here, and this is talking about the MCU conditions. This is figure 6 on page 12. And notice that it lists out a bunch of these conditions. And notice a couple of them, a lot of these have to do with batteries and BMS, but one of them is KSI, which is our key switch input, charge, and plug-in. So the KSI and plug-in, I think, will do what I need to hook up the logic to my output 4. So obviously we could see this KSI is set to 1, meaning it's on. And it would have to be set to 1 because I wouldn't be able to talk to the MCU I mentioned before in this terminal program without the KSI being on. What we need to do now is figure out how the proximity thing works. So I have the proximity and pilot wires connected from my charge port into the MCU now. I'm going to go ahead and plug in one of my J1772 chargers into my port. Let's see what happens. Okay, plugged in, but let's hit SH again and see where we are. Well, the proximity is at 150R. This is an interesting thing. I didn't know this before, but depending on the type of charger you're plugging into it, it will give a different resistance value to the proximity pin to tell whatever your car's system how much current can that charger handle. This 150R I think stands for 15K or something, or 1.5K. I can't remember what the value was, but that's the lowest level charger. In fact, this is my little 110 volt charger that came with my Volt. So it's likely only probably putting out about 10 amps or something like that. We do have proximity detected. We did have pilot detected because our charging trace started up, and so we know at least that our charge port is being tracked by the MCU, so that's good. Now let's use this information to set up our output 4. What we want to do now is set the output 4 to either the KSI or whether we're plugged in or not. So those are the two conditions. And what you could do is say set out 4 and then hit enter. And what it'll do is, because I forgot to set it to anything, it's going to output a bunch of help text to me. And so notice that it's got several examples, like set out 1 to fuel gauge, or set out 1 to temp gauge, set out 1 to high voltage, the high voltage condition, or not the high voltage condition. Or if you put two conditions together with a space between them, like set out 1 HVC high pack, the space between them is an or condition. So that kind of tells us what we need to do here. We need to say set out 4 to either plug in or KSI. Now notice when I set that, the contactor immediately clicked. And that's because once I map that output, it's going to happen immediately. And why did it click the contactors? Well, because I have the KSI on. So that's the condition there. So if we hit SH again, we can see that our output 4 is mapped. It not only is on or connected to ground, but these are the conditions, plug-in or KSI. What's interesting also about that is notice plug-in is in lowercase, but KSI is in uppercase. When you do a SH, it'll show you the conditions for that output, and it'll uppercase the one that's true and lowercase the one that's not true. So we're not plugged in, but we got the KSI. Now if I plug it in and the KSI is on, that'll still have it turned on, right? So what I'm going to do now is when I turn off the KSI, if I turn off the KSI, I'm no longer connected via the terminal program, and I can't issue commands or look at it. But what I can do is listen for that contactor click. If I turn off the KSI but plug it in and it still clicks, then we know we have that either or condition working. Let's give that a shot. All right, I'm going to turn off the key switch. Notice the contactor is now off and our prompt is sleeping. Let's go ahead and plug in the car. We're going to listen to see what happens when I plug in. And it clicks. So that's perfect. We've got our KSI or plug-in turning on our parallel battery packs. Let's move on to our next programmable output. All right, well, the second output we're going to program is the controller KSI. Right now, that's living in this terminal here on this terminal block. And if I put my test light on it, it is currently off. There's no voltage to it. The point of the controller KSI, similar to the MCU KSI, is it holds the controller on so you can actually drive the car. For the most part, I want it to be the same as the KSI that's going to the MCU, wherein if my key switch is on and that's also running through my impact or inertia switch, I want that to turn on the controller. But there's one additional feature that I want the controller KSI to have, and that I want it disabled if we're plugged in. The purpose of that is to prevent me from being stupid and driving off with my car charger plugged in and damaging both my car and the charger. If you've been watching my videos, you know that I previously had solved that issue using straight up wiring and a relay. That AVC2 had a little relay on it wherein if it were plugged in, it would output 12 volts. That 12 volts went into a relay that I removed from here that ran the common through the key switch and went to the KSI of the controller through the normally closed part of the relay. Well, when we're plugged in, the relay would close to the normally open port and essentially open up the KSI, whereby preventing the controller from turning on. Now that I have the AVC2 removed and that relay removed, we need to let the MCU do it, and we're going to do that with a programmable output, which will be much simpler than the previous implementation. To do that, we're going to use the special output 5. Now, remember when I mentioned output 5, unlike the other outputs 1 through 4, doesn't close to ground. Instead, it outputs a 12-volt signal. That 12-volt signal is in this pin right below it, that's in red here, which is the output 5 12 volts. Well, I didn't see a way to, in the programming, to do AND type Boolean logic, because what I wanted to do is say, if the KSI and it's not plugged in, then I want that output 5 to have 12 volts. But there's an easy way to get around that. What I did was, this input here for the 12 volts, I simply moved it from my constant power block to my KSI. And what I did is, on this terminal strip here, I've got 3 terminals all tied together, and that's my constant 12-volt battery power. And then these 2 terminals here are my KSI. And I just simply moved that wire over to my KSI. So that makes it to where it has to be an AND. If I enable output 5 by saying it can't be plugged in, then it outputs whatever the KSI outputs. Well, if the KSI is off, then it's still outputting 0 volts. So I think that'll be a perfect replacement to that. Now, the reason I'm using output 5, you have to be careful with that, because it does output 12 volts, but that 12 volts can't really do a whole lot. In other words, it only can probably handle up to maybe an amp or so. So you want to hook that output 5 specifically up to any device where the 12 volts doesn't really pull much current. And the controller KSI is a perfect example of that. That's just a 12-volt signal into a digital interface. It doesn't pull very much current at all, so we can use output 5 and not having to hook up any additional relays to it. Well, programming output 5 couldn't be easier. We're simply going to say set out 5 to not plug in. So we use the minus sign to do a logical not. That will enable output 5 only when we're not plugged in. So it's going to be pretty much enabled almost all the time. Now you can see in our show that output 5 is outputting 12 volts because we are not plugged in. Notice that plug-in is lowercase on our positive condition, but it's uppercased on our condition here because this statement not plugged in is true. So let's go to the back and check to see if we have 12 volts now going to our controller KSI. So our ignition switch is on, our KSI is on the MCU, and we're not plugged in. So if we put our tester on here, we could see that we are glowing, we have 12 volts to our controller KSI. If we plug in, that should have disabled our KSI. Let's see what happened. And in fact, we no longer have our KSI. Well, okay, in conclusion, what have we learned in this video? Well, we've got the MCU completely wired up. We learned how to wire it. We learned how to connect our laptop to it, issue some commands, and get some information out of it. Not only that, but we learned how to program some of the customizable outputs. In regards to the MCU being the brains of our EV, we have verified it is controlling the charge port, it is controlling our battery contactors, and it is managing our KSI on our controller with the plug-in disable. So we're getting there. Now in the next video, what we're going to do is hook up the charger wiring in the back and all the wiring for the measuring balancing boards for the BMS. And we're going to get that all connected into the MCU. Our goal for the next video is to do a full balancing charge and ensure that the MCU is now controlling our complete charging system and charging our batteries properly. So stay tuned for that next video. If you haven't subscribed to my channel already, go ahead and do that so you can get notified of that next video. And until then, I'll talk to you later.